Welcome, students, to this explainer. I'm absolutely thrilled you're here with us. Today, we're tackling a super important foundational topic in your CSCE Chemistry syllabus, rates of reaction. Now, I know chemistry can sometimes feel, well, a bit abstract, but I promise you, by the end of this session, you're going to see exactly how these concepts apply to the real world, and more importantly, exactly what you need to know to ace those exams. Let's get right into it.
Okay, let's dive into this. Have you ever had a headache, dropped a solid pain relief tablet into a glass of water, and just watched it slowly fizz away? Now think about what happens if you take that exact same tablet, but you crush it into a powder before dropping it in. It violently fizzes and just disappears in seconds. But why? Why on earth does the exact same amount of medicine react so much faster just because it's crushed up? Well, that right there is the magic of reaction rates.
So, here's our roadmap for today. We'll cover what is reaction rate, the factors affecting the rate, experiments in action, understanding the graphs, CSEC exam tips, and finally, a summary and quick check. Section 1. What is reaction rate? Defining the basics. According to Section 10.1 of your CSEC syllabus, you literally need to know this exact definition word for word. The rate of reaction is the change in concentration of reactant or product with time at a stated temperature. Think of it kind of like driving a car, right? Your speed is just how your distance changes over time, while in chemistry, the rate is how your chemical concentration changes over time. And this brilliantly illustrates exactly what we mean. At 10 seconds, you can see the reactant concentration is really high. Then at 20 seconds, it drops. And at 30 seconds, it drops even more. As time ticks by, those reactants are being used up to make products. Basically, the faster that concentration drops, the faster your overall rate of reaction is. Moving on to Section 2, factors affecting the rate. What exactly speeds it up? Your syllabus lists 4 main factors here. The very first one is concentration. So imagine a super crowded hallway between classes. If there are, say, 100 students in the hall, people are going to bump into each other a lot, right? That is high concentration. But if there are only 10 students, you'll naturally have way fewer collisions. It's the exact same in chemistry. More crowded particles mean more collisions, and more collisions mean a much faster reaction. The second factor we need to look at is surface area. And honestly, this brings us right back to our crushed tablet hook from earlier. See, a large chunk of solid only exposes its outside layer to the reaction. All those particles trapped inside, they can't react yet. But the moment you grind it down into a powdered solid, you instantly expose millions of new surfaces. More exposed surface area means way more room for particles to collide, which greatly speeds up the reaction. Now, your syllabus actually includes a very specific and kind of scary real-world warning about surface area. It explicitly states you must consider, and I quote, the danger of explosive combustion of finely divided substances, for example, flour in flour mills. I mean, flour seems completely harmless, right? But when it's a massive cloud of tiny dust particles floating in the air, its surface area is absolutely enormous. Literally just one tiny spark can cause all those suspended particles to react with oxygen instantly, leading to a massive, devastating explosion. No way, right? But it happens. Now, what's really interesting about this slide is how we map out the final 2 factors side by side, temperature and catalysts. For temperature, adding heat simply gives the particles way more energy. They zoom around faster and they collide a lot harder. A catalyst, on the other hand, provides a completely different chemical pathway, one with a much lower activation energy. It basically gives the whole reaction a super convenient shortcut, so it can happen easier and faster, all without the catalyst itself ever getting used up. Section 3. Experiments in action. Testing the factors. The syllabus explicitly lists 3 specific practical exercises you absolutely must know. First up, adding magnesium strips to dilute acid. Here, you'll clearly see bubbling gas, and you can actually measure just how fast that gas is produced. Second, reacting marble chips with dilute hydrochloric acid. For this one, you can alter the size of the chips to directly test the effect of surface area. And third, sodium thiosulfate mixed with dilute acid. This reaction creates a cloudy solid, and you literally time how long it takes for a cross drawn on a piece of paper beneath the flask to completely disappear. All right, Section 4, understanding the graphs, visualizing reaction data. Now, I know this is where a lot of students start to panic, but trust me, you won't. Right here in section 10.4 of the CSEC syllabus, it explicitly states you must interpret graphical representation of data obtained in studying rates of reaction. It sounds super formal, but let's just break down the first one nice and simply. So, the crucial point is this. Whenever you look at a graph showing concentration, volume, or mass on the side axis and time on the bottom axis, you really just need to look at the slope of the curve. A steeper, sharper slope directly means the reaction is happening very, very fast. And as you see the curve start to flatten out, well, that just means the reaction is slowing down because all those reactants are finally being used up. And, the syllabus also notes two other specific graph types you really need to master: concentration versus 1/time and simply rate versus time. In a rate versus time graph, you'll always see the line start way up high. Why? Because the rate is at its absolute fastest at the very beginning of the reaction. Then it'll steadily drop down towards zero as the reaction eventually stops. Section 5, CSE exam tips, how to actually get those marks. Lesson, knowing the facts is really only half the battle. Knowing exactly how to write them down for the examiners is the other half. When an exam question asks you to explain why a reaction is faster, please don't just write "it's hotter." You have to use your keywords. First, state the factor clearly, and then explain it using particles. Write down things like increasing the temperature increases the energy of the particles, or crushing the solid increases the surface area, which increases the frequency of collisions. That right there, frequency of collisions, that is an absolute golden phrase that examiners literally love to see. It'll get you full marks for sure.
Section 6, Summary and Quick Check. Time to test your memory.
Okay, I want you to actively think about the answers to these before I reveal them. Ready? Here is Quick Check 1. According to the syllabus notes, we literally just covered what happens to the rate of reaction as the reaction proceeds. Take a second to think about it. Does it stay the exact same? Does it speed up? Nope, it slows down. As the reaction proceeds, your reactants are getting used up, so the rate naturally decreases until it eventually just stops. All right, quick check 2. The syllabus specifically ties chemistry over to biology under the catalyst section. Can you name one biological system that acts as a catalyst? Think about it. If you said enzymes, you are absolutely correct. Enzymes are amazing biological catalysts that speed up crucial reactions in our bodies, all without getting used up themselves. Let's move to the next slide and see how this all builds into our final picture. Here is your master summary recap chart. We've got our four main factors. Concentration brings more crowded particles. Temperature brings faster, much more energetic movement. Surface area exposes way more particles for the reaction. And a catalyst provides a completely easier chemical pathway. The big takeaway? Every single one of these factors leads to more successful collisions and therefore a faster rate of reaction. Which leaves us with this final kind of crazy thought. We talked earlier about how the massive surface area of finely divided flour can cause literal, devastating explosions in flour mills. So look around your own kitchen. If simple, everyday flour can react that violently just by being dispersed in the air, what other seemingly harmless powders in your pantry might be hiding explosive reaction rates? Think about it. Thank you so much for joining me today for this explainer, and definitely keep exploring the chemistry all around you.